You're saying that's just right. Really funny. Yes. Just roll the piece. Still.
Anything else? All right, let's continue. Actually, I'll make one small step back to discussion of this equation. So, remember what I finished with. I finished with the concept of compressibility or incompressibility. And I mentioned that this has nothing to do with fluid mass. It is to do only with fluid volume. Fluid volume essentially is a geometrical thing. Right? So size of the object, that's what defines the volume. Right? Dimensions. So how wide, how long, how deep. So, and if we are changing the size of the object, we actually, the way we do that, we are moving the size of the faces of the object, right? The winners and the object. If you have a box, how do you make it more larger or bigger? Well, you have to take the walls and either move them in or out, right? So, therefore, the concept of changing the volume, which means the concept of compressibility, is associated with the physical motion. Motion is characterized by velocity. So that's what incompressibility is, that motion is such that if you squeeze something in one direction, it bulges in the other direction. Right? That's what that means. So this is to do with the velocities, the velocity field, not with the amount of mass inside. So, but what I would like to do is to see what actually happens if I do state that I consider incompressible fluid. What happens to this equation? So, remember, previously I asked the question, what happens if density is constant? So all this is zero, and therefore we conclude that this must be zero as well. Now I stated the other way around, logically opposite way. I ask, what happens if I state that the fluid is incompressible? And in this case, you have to start answering the question backwards. Incompressible means that. That's what it means. Okay? So it means that divergence of velocity field is zero. But then, if this is so, then the right-hand side of this equation is zero. And this has nothing to do with fluid density being constant or not. Because the combination of density and velocity might as well be such that things balance out. So, for example, if density increases in x direction, so this derivative is positive, and u is positive, but density decreases in y direction, and v is positive. So therefore, this is positive, this is negative. You add them together, they might cancel each other, right? And you will still be able to get the right-hand side zeros. So, but let us look at this equation here. So what does it look like? We've seen this structure already on the previous slide, or on the previous board. Can you see anything like that? Can you remember seeing anything like that? Let's just try to scroll back. So, yes. Can you see anything similar?
Yes, that's question.
And the only thing which has changed is instead of u, I have rho. Right? It's exactly the same structure, except instead of u, I have rho. So essentially what we have here is so-called material derivative of the density. And remember what material derivative does? It shows you variation as decomposed in two parts. One associated with the local variation. The other one is associated with the movement.
Okay.
So essentially what you have here is, if the fluid is incompressible, so that's what you are left with. And this is nothing else but material derivative. So material derivative is equal to 0, and that means that there are two contributions to change. One is local, one is global. So therefore, if you have, for example, d rho by dt positive, so somehow you're adding salt to water in this particular location. What happens to it? It dissolves, and once it is dissolved,
it
flows away, right? So you add salt here, but it goes away. So overall, nothing changes. You put it in, but it goes away. Okay? So that's what that means. So therefore, even not uniform density can result in incompressible incompressible condition. So that is something I wanted to emphasize. This is a simple concept, but unfortunately, in my experience, a lot of even lectures do not really put sufficient explanation of this fact. So compressibility has nothing to do with density. Density can be not constant, and still the fluid could be incompressible, salt water. Right? So that's something to keep in mind. Are there any other questions about this? Did I answer the question? Okay. All right. So, where to from here? Let me just look at my notes. All right. What I will do next is going to be relevant specifically to fluid. So far, what I've done here is more or less general, right? Newton's law. So what will follow is going to be relevant to fluids. So let me write down a system of equations, ordered equations, that we have derived by now. So it is rho dv dt plus v dot nabla v is equal to minus gradient of pressure plus rho times g. And the condition is equal to 0. So the divergence of velocity field is equal to 0. So V in this case is a vector consisting of 3 components.
Here you go.
Gravity is generally also a vector which consists of 3 components. So this combination here is, remember this big expression which I have written here. So, believe me, if you simply use basic vector calculus operations, if you define then the vector nabla, gradient vector, and use dot product. Remember what dot product is? If you have two vectors, so dot product between the first times first plus second times second plus third times third. Okay, so that's very simple. So I leave it for you as an exercise just to check that if I introduce this vector, and if I multiply and consider dot product of this vector with u, v, and w, and you apply this, so obviously dot product will produce some scalar, and you multiply the velocity vector v by this combination here, you will get what we tried previously. Okay? I'll leave it as an exercise. So it is a standard exercise in vector calculus. So some of you already are familiar with it. Those of you who are not familiar, just try and see that this is indeed the case. So shorthand notation. So, okay. consider 2D flows. So what is 2D flow? We live in three-dimensional world, but sometimes we have very wide rivers. Okay? For example, rivers. So then, if you're in the middle of the river, you look left, you look right, and you don't see the banks of the river, right? So my native city is Ulyanovsk, which is located on Volga in Russia. So Volga, where I live, is about the narrowest place is 4 kilometers wide. So, and downstream it's about 15 kilometers wide. So if you're on a boat in the middle of it, you hardly can see anything on either side. So in that case, clearly if you don't see anything on the side, so if you move left or right by a couple of meters, nothing will change. So in that case, we can say that we can claim that something happens downstream and something happens to the depth, but not much change happens sideways. So that's the situation of two-dimensional flow. So if the flow is like that, so a typical example is the river flow. So then we have on the x and y coordinates, so z is not there, so we don't need that. And we want to have u and v. So I would transpose, getting that to the vectors are written in column, but I could just save space, I wrote it like that. And this becomes du by dx plus dv by dy is equal to 0. That's the continuity equation. So, what is typically done or frequently done? We introduce an extra function which we call stream function. And it is defined like that. U is equal to, so just there are multiple ways of defining that. I'll just check what I use in my notes. So, deep psi by dy and v is equal to deep psi by dx negative in front of it. Okay, so those of you who studied in sort of fluid mechanics before would know. So why? So for those of you who haven't seen that before, what's the trick here? So all right, this is the continuity equation. So if we take this and substitute there, so I will get d squared psi dx dy. That's substituting u in there. And substituting v will give me d squared psi dy dx. Well, the only difference is that the order of differentiation, which we know does not affect anything, clearly this is identically equal to 0. So if we rewrite equations not in terms of components u and v, but in terms of stream function, then all of a sudden this equation will disappear. It is already defined as 0, so therefore we don't need to solve it. What means? Well, looks like a good idea, and the question is it just a freebie? If we just do that, and then we don't worry about, well, essentially, we have to solve 4 equations, but one of them is essentially solved by this simple substitution. It means that we simplified our life significantly by 1/4 out of 4 equations. We got 25% reduction in cost. Yeah. Well, the saying, when something feels too good to be true, right? Okay, exactly. So, just before we go ahead with this, so a question: what do you think the price we will have to pay for that? So we sort of saving ourselves 25% of work by getting rid of one. Well, in 2 dimensions we actually have 3 equations, and we got rid of one of them. So with this 33% reduction.
It is. It's 20 minutes. Same.
What's the price and where does it come?
Understood. The next stuff, and the river weight is not that large, I guess. Okay.
All right, I'll help you. So one thing which I did not mention at any point at this stage. So I talked about equations. We derived the equations. We discussed the equations. We never talked about how or what we need to solve the equations. So we are dealing with differential equations. So, and differential equations, they require something else to be solved. Boundary conditions. How many boundary conditions do we need?
Or follows.
Well, it depends on the type of equation. So, boundary conditions, the number of boundary conditions is dictated by the number of derivatives, right? So, you count the functions, you count their derivatives, and you count the total number of equations. Now, if we look at this equation, so what is the highest derivative for each of the components u, v, and w?
Well, that's the big way to saving what sort it.
First derivative, right? First derivative. So therefore, we have, say, u and v components, right? Each of them have their own derivatives, first derivative. So therefore, we will need to specify two boundary conditions for u and v. And what do you think the physical boundary conditions could be? Like physically, when you consider the flow of fluid within some boundaries, so obviously if we're talking about boundary conditions, we need to say what happens at the boundaries.
I know.
What happens at the boundaries?
Doesn't stick to you on the
We are talking about inviscid fluids. Now, friction is not a factor. At this stage, we cannot say does not stick, but we can say
no penetration for waste.
if it is inviscid,
Go on.
so no tangential stresses there. We come back to stresses. So stresses are not there.
So non-model. Just
What am I showing?
normal. Anywhere in this little verse. Actually, pushing maybe
If it is a wall,
no fake is
no solid wall, no penetration. So fluid cannot flow through the wall, right? So that's right. So the normal condition, perpendicular, the fluid velocity in the direction perpendicular to the wall must be zero. Okay? And this is written.
so good.
Again, this is from vector calculus. Dot product between the direction of the velocity
To the normal.
and the direction of the normal, they fall 90 degrees. That the fluid means that that fluid flows along the wall, not across the wall. So that's the initial, the boundary condition. Right. When we introduce this beautiful function, what actually happens with the equation?
Yeah, maybe. Shit, I watched because
So u has its own derivative,
too much.
but u is a derivative. So it is a derivative of a derivative. So therefore, if I were to replace u in this equation with the dy by d phi, and then I would need to differentiate that once again because we have du by dx, right? So therefore, what we will do, we will essentially increase the order of the equation. We used to have a first order differential equation, but when we rewrite it like that, we will have to have second order differential equation. Yes, we will get rid of continuity equation, but we will still have to add extra equations because of the boundary conditions, right? So you will have to add. So it is not freebie at all, right? So, but nevertheless, it is a common practice, especially in the 20th century. It was a common practice to make analytical progress, to derive equations written in terms of stream function. Okay? And we will follow this historic idea. So, simply because if you ever need to review what I'm talking about, you will be able to refer to these historical books. Okay, so, but I'm telling you in practice, in my own practice, research practice of 21st century research, you don't really do that. You stick with U, V, and W. So it gives you much more diversity. That's already common fact. So, but for historical reasons, we will introduce stream function, and we will do something with stream functions. But later on, I will abandon this idea, and I will show you a 21st century approach later on in the second half. All right, that is this. So, now, let us count how many physical parameters enter our system of equations. Okay? So, this is our system of equations. We have U, V, P as unknowns, right? These are the functions. Even if it is two-dimensional, there are three of them. Okay?
So,
we have rho. We state that we do not, we assume that rho is constant, so it is given just for simplicity. In general, it cannot be, it might not be constant, but we just state with to start with that rho is a constant. But you still need to specify its value, right? If you want to solve a physical problem, you need to know what that is. If it is water, then it is 1,000 kilograms per cubic meter. If it is petroleum, then it is 900 kilograms per cubic meter, something like that. Right? So, gravity. Well, nowadays, and especially in countries like India, where the space program is truly taking off, what used to be dominated by Soviet Union and the United States, but now I think the Soviet Union, Russia is, well, it still has program, but China and India are becoming the major powers in this space race nowadays. Well, but once you leave the Earth, what happens with gravity? Changes, right? So therefore, it is a matter of that needs to be considered now, right? So gravity has to be taken into account. If we're here, we're fine. We can say that it is in international system. It is 9.8 meters per second squared, right? But if you move to equator, it will be less than that. Move to North Pole will be more than that. If you go to outer space, it will be close to zero. So that is a legitimate parameter which we need to know. We talked about boundary conditions, right? So boundaries, well, they have some sort of genetic description, right? So that's a black wall, or it is a curved wall, or it is a spherical wall, or something like that, right? So, and not only that, but also we need to say, well, if this is a channel in which the fluid flows, how wide that channel is, right? So geometry is still there. So, and obviously, if you consider flowing this channel or this channel, you will get different solutions, right? So, next thing is flows developing time. If you consider just instantaneous field, that's one thing. If you consider the same field, the evolution over 4 or 5 hours, it's a different thing. So time is, or length of time, is a parameter. So even though there are only, say, 3 equations here, algebraic equations, the number of parameters were already counted how many? Of time, gravity, density, geometry. So, and I didn't mention anything about pressure. So, for example, we can create a flow by essentially using a pump, which will create the pressure. So, therefore, pressure also has a parameter, some sort of parameter. So, you can see that even though it is a standard set of 3 equations only, in reality, you modify them. Every single situation, physical situation, requires essentially will modify those equations. And if you think about it, every time you modify that equation, you have to solve those equations once again. So, at the very least, this is time-consuming. At the very least, time-consuming, and nowadays time is money. It's expensive, Right? So therefore, we need to look for the ways to somehow make our life easier. So we do not really have enough time to solve all the possible problems that we might face in our life. We need to think how we can solve this problem, multiple problems at once. Okay, and that is the next thing which is relevant to fluid flow modeling, but equally valid to any physical modeling, no matter what the situation is, whether it is solid mechanics, chemistry, anything which requires specifying physical quantities falls into this category of physical problems. And that is something which we need to know how to deal with. Again, this has nothing to do with fluids. It is generic, completely generic situation with any physical or engineering problem. Once you come up with a physical system of equations, the next step is to solve them, and to solve them you need to apply boundary conditions, so you need to come up with those, and once you came up with those conditions, you still need to look for methods and ways of economic and robust solving of those system of equations. So, one thing I always teach my students, I have a lot of engineering students, my university physics students, and somehow, I don't know how it is here in India, but somehow in the Western world, in Australia, for example, it doesn't sink in that you never solve equations, physical equations, the way they give it. Never. And some of you might already realize which way I'm going. So, what do you think I will be talking about next?
Nondimensionalisation.
Nondimensionalisation. Exactly. So we need to scale our equations. Any physical equations have to be scaled before you can solve them mathematically. If you're a mathematician, you can sort of try to solve whatever you are given by physicists, and you invariably fail. You have to scale the equations first. And again, I will go through this process because it has an interesting mathematical feature. So how do we do that? So non-dimensionalization. So more details are in my handwritten notes. But I will put the very brief description of steps on the board, and then we will be able to read the more detailed discussion in the notes. So first, identify the relevant physical quantities. So, and these fall into several categories. So, categories depend on physical area of physics, on the type of problem, but the idea itself is quite generic. Solid mechanics will follow the same exact idea. So what are they? So first thing is quantities that characterize the geometry, the region in which you need to find the solution. Okay? Geometry.
That's it.
And for geometry,
So,
let's say some sort of L. For example, the width of the channel. If we consider a channel or river, width or depth of the river. Okay? So, this is called characteristic length. So, if we are talking about the flow, let's say, in the medical syringe, so the scale, there are two scales there, in the needle, which is microscopic scale, and in the syringe itself, just before the piston, in front of the piston, right? If you are talking about geophysical applications, like for example hurricanes, we are not talking about 1 millimeter. We are talking about thousands of kilometers, like hurricane, for example, right? So therefore, we are not interested in what happens over in the hurricane in the distance over distance of 1 millimeter. Doesn't make any sense. over a couple hundred of kilometers, yes. Right? So that's this. Then we need to identify quantities that describe the object of study, fluid. So, what do you think out of all parameters we discussed so far? Which one do you think is attributed as to describe the fluid itself?
Density.
Density, right? Fluid. So therefore, density. Later on, we will see that something else is needed to describe viscous fluid, some viscosity, but that will come later. So describe geometry, describe fluid. In solid mechanics, for example, you will need to describe the material, right? Elasticity, for example. So next thing is you should have some sort of physical expectation of what you want to get. So you're talking about flow, right? So you expect something to get out of the flow, right? If you're talking about hurricane, you do not expect the velocity of a hurricane to be 1 centimeter per second. Right? You expect it to be a hurricane speed of 100 kilometers an hour, maybe, right? Or 200, right? So that's something like that. So, and clearly the flow, so the process in which the fluid is involved, right? That is characterized by velocity, right? So, what else is there? So, what do you think? What one more important?
Pressure.
So, yes, flow will not exist on its own. It has to be force. So, characteristic of the force. And in that case, it is pressure. Any other things?
Convex types, the plates of connects.
So, what forces did we introduce here? So, pressure force, gradient, and gravity, right? So, gravity. So, these are the physical quantities which somehow characterize our problem. Okay? And these are the 4 main categories. Next thing is dimensions.
Nice.
Excuse me, sir.
Yes.
So why aren't we talking about the characteristic type?
Time. Yes, that goes here.
Yes, that's good.
Thank you. So this characteristic of the flow. So flow is observed over which time? Right? Thank you very much. Very good addition.
Yeah.
So second step, dimensions. So units and dimensions. So do you know the difference between units and dimensions?
Yeah.
So what is unit? Give me an example of a unit and give me an example of dimension, if you know.
So the unit of the dimension length would be meter or centimeter or something. So units could be like different depending on the thing that we are measuring. For example, I'm talking in terms of length, but the dimension of all these units would be the same, the length.
Correct. So length, that's dimension. 1 centimeter, 1 millimeter, micron, angstrom, kilometer, mile, nautical mile units. Okay, same thing is described differently, right? So therefore, if you're a physicist or if you're an engineer, and if somebody tells you that the solution of the problem is that length is 5. 5 for what? Right? Kilometers or millimeters? Big difference, right? So therefore, any practical problem has to be solved keeping in mind that the answer, the numerical answer, is meaningless without units. But at this stage, we're not talking about units, we're talking about dimensions, fundamental dimensions. So fundamental dimensions which are relevant to our type of problems, solid mechanics, or fluid mechanics, any sort of mechanics, to be length, time, mass, what else?
Temperature. With temperature. But
Temperature, we're not considering it here, but yes, temperature,
time.
time. Anything else you can think of? Just maybe we're not going to touch other ones, so that's fine that we will be dealing with. But what else is there? Do you remember? From chemistry, for example.
Moles.
Moles. So moles, it's a unit actually. So it is a quantity of material, essential substance. The amount of substance, right? So, and one more, at least from light physics. Luminosity. And so that's just brightness of light. So again, we are not going to go there. Right? So in our case, it's just 5. So dimensions. So we need to determine the dimensions. Then how do we do that? Well, there is a special notation for that. L. So that's the first quantity here. So L has dimensions of length. Let's say we denote it by L. Okay, so L is actually a physical quantity which has 2 things attached to that. L is numerical value plus units. But the dimensions is just 1, length. Okay? Good. Next one, density. What is it? It is mass per volume. Volume is not independent, right? It is length times length and length, or length and width and height. So it is M, L, and I write it like that, it would be easier for us to handle that. All right, so what's next?
This.
V.
L.
L.
And T.
T minus 1. So, by the way, what I would like to do, so this is quite a typical problem that I ask of students to complete. So, therefore, I suggest that you write, not only listen to me, but write down what I'm doing here, and then I will ask you to do something for me. So, we will consider this part as a part of tutorial as well. Okay, so I sort of use a blended mode of teaching when I have lectures which flow into tutorials. Tutorials become lectures. So sort of just the physical time will be limited to 4 hours for today. So, but how we distribute that between lecture and tutorial will just play by ear. So, all right. So I'm writing this, but later on, in a few minutes, I will ask you to do something. So VLT minus 1. So next one.
Good.
Thomas. Yeah.
So I probably should be careful here. So this is what we have in our equations, lowercase t. So therefore, and therefore here I will have units for t.
Well, this.
Clearly just t. All right.
Wow.
What about pressure? And this is something you need to work a little bit harder. So, how do you know what the dimensions for pressure? So, and the way to decide what that is force. Remember the physical definition. Pressure is force per area. Okay, let's do it one thing at a time. So it is force. And for the time being, I forgot what that is. Pretend that I forgot what it is. But it is per area, and I definitely remember what units for, dimensions for area are.
It is like
It is L squared, but it is goes per area, so therefore it is negative. Okay? Alright, good. So now going back to force. So if you forgot what it is, well, remember some physical law, Newton's law, mass times acceleration. Right? So this is mass. Clearly for mass, we will have dimensions of mass, m. Acceleration, it is velocity per square, and which means that is velocity is distance per time. So distance per time. So which is L.
E minus speed of light, so
t minus 2, right? And L minus 2 is still there, so overall now we will get that this is M
in these two.
L minus 1 t minus 2, right? Okay, so anything else? Gravity.
You can L3 minus 2, L3 minus 2.
So it is L t minus 2, right? So, all right. So we have that list of suspected influencers. We translated them into their own dimensions. And what I would like to do next is to lead you to what is known as a pi procedure.
No.
So pi procedure is based on Buckingham-Pi's theorem. And did anyone hear about that before? So just raise your hand if you're somehow familiar with that, with these names. Buckingham-Pi theorem. All right, not many of you. So I'll state what it is. So the theorem, mathematical theorem, really tells us that we can reduce the description of a problem containing that many parameters to a problem equivalent, completely equivalent problem containing a lot less parameters. So that's a very loose interpretation, but that's the essence of the theorem. And this is guaranteed to work provided that the parameters are chosen correctly. Parameters have to be chosen following the so-called pi procedure. And that is the procedure which is introduced in different books, different way. I would like to introduce it in a rigorous mathematical way, so I know for sure that it is going to work. So some of the items in this procedure you will find familiar with. Some of them you will need to relate what we are doing with the concepts of linear algebra. Okay, so and I will tell you what I mean as we go. So, okay, so
Is it?
I don't want to go to the next page, so I will probably just use this space here to form the starting point for pi procedure. So what is pi procedure? So how does it work? Pi procedure tells me that it is possible to create non-dimensional group in such a way that it will contain the physical parameters, dimensional parameters. Somehow we can combine those things and we will be able to create a non-dimensional group out of them. So some products or ratios or powers of these dimensions will cancel out magically and we will end up with some sort of non-dimensional group, which we will call non-dimensional parameters. So then I will explain why we need those non-dimensional parameters later once we get there. All right. Before I go there, though, I would like to mention to you one obvious thing that sometimes it gets forgotten, especially by pure mathematicians. What I mean by that is the following. If we are claiming that the system of equations, or just an equation, describes a physical phenomenon, not just abstract mathematical equations, but physical phenomenon. So equation contains sum of terms, and equations contain necessarily equal sign, different side, left-hand side, right-hand side. So equation can only have physical meaning, or can only be physically relevant, practically relevant, describe physical reality, or reality at all, if all terms that are being added in the equation are dimensionally consistent. Right? So, for example, if I have A plus B and A represents apples and B represents oranges, when I add them together, I will get fruit salad. I don't get apples, I don't get oranges. And then that's pretty much be my guess to decide how many oranges, how many, so pretty much everything becomes very subjective because it depends on taste, whether you like it or not, whether you put too many apples, too many oranges. So, no, but if you say A is 2 apples and B is 3 apples, when you add A and B, you'll get 5 apples. And nothing else. Okay? No ambiguity. Okay? So that's the basic principle. So if you have a physical system containing multiple parameters, and if these parameters all boil down to the same group of dimensions, that's okay. If you're adding apples and oranges, if you add kilometers and kilograms, or if you take a log of 5 kilograms, another thing, completely meaningless. Right? You cannot have sine of 5 kilometers.
Yes.
Sine of 5, that's the only thing you can get. So therefore, whatever you get physically has to have no dimensions if you want to substitute it into the sine function. If the frequency is 5 hertz, sine of 5 hertz does not make any sense. Sine of 5 hertz multiplied by 1 second becomes sine of 5. And that makes sense. Okay? So, all right. Anyway, so we create the following computation. We have all these quantities, and we list them in the order of appearance, for example. I will just copy them here, low, L, row. So leave some space in between, because we will need that. So what else we have here? Well, I'll just copy my lecture notes so that I have the same order, so that we will have the answer consistent with the notes. So it is a slightly different order to what we have here, but this is what you will see in my notes once you download them. And then you attribute powers to all these quantities. So how many of that do we have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 of that. So A, B, C, D, E, F. Yes. And then we claim that dimensions of this group are non-existent. So that's just noted by that. So it is non-dimensional. It's not attributed any dimension that is attributed to this combination. So this is called non-dimensional group.
Yes.
So your task is take this, combine things together, and tell me what the cumulative powers of each individual dimensions that are present are. So what I mean by that, so if you have density multiplied by velocity, you will see that it will be m multiplied by L minus 3 multiplied by L multiplied by t minus 1, right? So L minus 3 and L will give you L minus 2 cumulative, right? So, and once you've done that, you will see that each of these fundamental dimensions, M, L, T, we don't really have anything. We have only 3, M, L, and T. Okay. They will have some sort of monster sitting there as a power. And mass cannot cancel length. So the monster has to be equal to what? So I mean the cumulative power. If the dimensions are to disappear, the cumulative power of each dimension will have to be what?
0.
0. So therefore, here we go. So your task is to substitute these dimensions into here, keep the powers, then combine the powers coming from different terms, and tell me what the cumulative free expressions are going to be in terms of A, B, C, D, and E, and F. Okay, I'll give you a few minutes, and once you finish, you just let me know, and we will continue from that point.
See.
So, and if you have any questions, if you're still confused about what I'm asking you to do, let me know, and I'll help you individually.
Yeah. No, ways. Yes. But it's a tomorrow. Yes. And still sugar. And sausage. There you go.
Thanks, but
Well, yeah, that's it. And say she could swim instead of this. It's and share all the West. And you see that zero. You should face this. It's the same. Does it question? Jeans.
So, whenever somebody finishes, at least one yeah.
So we got 3 equations.
So you will have an equation containing powers for M, for L, and for T. 3 equations. But each of the equations will contain A, B, C, D also.
It will be equal to 0.
And the sum of all these has to be equal to 0.
Yes.
That's correct.
We've got this. Should I?
All right. I will create a new screen, and you will dictate it for me, and I will
Just
Inside killing.
write them down. So, and I will write them down. So, the first one is for what quantity?
this is for L.
L.
So it goes like A minus 3B
A minus 3B
plus C
plus C
plus D
plus D
minus E equals 0.
equals 0. Correct. Yeah, that's what I have. Right? So, next one.
M. The B plus E equals 0.
B plus E is equal to 0. And the last one?
This for T. This is C plus 2 times D plus 2 times E minus F equals 0. 2 times E minus F equals 0.
Alright, so this is the system of equations that we got. Before we move on, I need to make sure that everyone gets the same thing and that everyone understands what we did. So if anyone is not quite clear about it, let me know, because this is a crucial point. Yes?
try to understand.
I mean, how to solve it?
Not how to solve it, but did you derive this?
No.
Not yet. All right. So let me just go back. And so we start with this. We formally list all these quantities as a product, and we assign some powers to each of these.
Same.
Right? So then, for example, we start with L. So we have L, this L here, raised to the power A, which means that we will have L to the power A. Is that clear? So this L has dimensions of this capital L, but it is raised to the power A. Are you with me?
Yes.
Right? So just let me know. So then, the next one is rho. I'm looking here, M multiplied by L to the power minus 3. So it is rho to the power B. So M to the power B, it will be M to the power B. And then L minus 3, L to the power minus 3B. Right?
Works.
Okay, going further, V. So let's look at V, where? Here we go. V has LT minus 1, and it is raised to the power C. So it is L to the power C,
You.
and multiplied by T to the power minus C.
Comments.
Right? So next one, P. You have this. So this is your final expression for P, but it is raised to the power E. So therefore it will be M to the power E times L to the power minus E plus multiplied by T to the power minus 2 times E. And finally, T to the power F. So it will be T multiplied by, sorry, this G, and then T. So all the same. So that's the principle. Is that clear? So I put dot 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 here, so just to be continued.
Thank you.
Okay? All right. So is everyone else clear what we are doing?
So,
Okay, good.
wait.
Was
So now if you look at the cumulative power, so L,
So,
basically what I mean here is the following. So you can see that L appears multiple times L to the power A, L to the power minus 3B, and so on. So I collect L powers of all L. L, A minus 3B plus C, and so on. Right? And that's what I have here.
Be honest. Really.
That's just the power of L. And I do the same with M, and I do the same with T. Okay? All right. So now we will formally write this system of equations because this is algebraic system of equations, right? Linear equations
See this way.
with a catch. And what is the catch here? So how many equations do we have here?
6.
How many unknowns do we have here? 6. Right. So this is so-called underdetermined system of equations. So, and we need to know how to solve that. And those of you who can remember a single example from linear algebra, they can remember that this is described from keywords like such as rank deficient matrix, or rank is less dimensionality. All sorts of things like that happen here. So, but the bottom line, no matter how you call it, how you term it, the idea of solving this is by parameterization. And that's how we proceed. So I'll show you how to write it down in a suitable parametric form. And then I will guide you through the solution. But hopefully you will be able to do the actual solution on your own. So, all right. Once you get this system of equations written in just coefficient form, I would like you to rewrite this in a matrix form. So, and to rewrite it in a matrix form, we need to essentially introduce the vector of unknowns. So, what do you think I mean? What do you think I mean by vector of unknowns? What are the unknowns in this system?
That means to be
A, B, C, D, E, and F. Right? So therefore, I will have a vector, or that will be
choose
A, B, C, D, E, and F. So this is the vector of unknowns.
Good.
In the right-hand side, I will have also a vector because I have 3 equations. So what will I have on the right-hand side?
0,
How many of them?
3, 4, 6, 3,
Right? Okay. And what will I have here? So coefficients which appear in front of unknowns. So what is the coefficient in front of A?
1,
Join.
3.
Next one.
I just find 2,
Next one.
4,
Next one.
and
Next one.
10.
0.
0. Next one.
Not here, in the first.
F. Yeah. Yes. So A is 0. Next one.
1,
1. Next one.
He sings it.
5,
So remember that is A, B, C, D, E, right? So there is no C there, so therefore it is next one, next one, next one. Okay, final,
You're writing to you.
first one,
0,
next,
0,
next,
1,
next,
2,
next,
2, 0,
and the final,
minus 4.
minus 1. Okay, is that clear what we've done?
Yes. Yeah.
Okay, so what we see here is, oops, a system of equations that is written in a matrix vector form. Matrix has dimensions of how many?
3 cross
3
cross 6.
by 6, right? 3 rows, 6 columns. It is multiplied by a vector which has dimensions of what?
6 particulars.
6, 1. So, middle dimensions, the same, 6 and 6. And they cancel, right? So it's just, and because of that, you will get the first dimension borrowed from the first dimension of the first matrix, and the second from the second, from the second vector, right? So therefore, what you will get is 3 by 1. Okay. So, and we are coming to a close of this lecture, so I will just say what we want to do, and then we will stop for a break. Now, this is a system of 3 equations for 6 unknowns, undetermined system. So we can only solve it by declaring some of the unknowns as parameters. And parameters are still unknowns, but we treat them as if we know them. So that's sort of confusion, right? Creates some confusion. So these are unknowns, but we think that we know them. And we treat the other unknowns as unknowns, and we find those unknowns in terms of known unknowns, which we call parameters. Right? After the break, I will continue with showing you how to proceed formally with this.